Welcome! In this video, we'll explore LeetCode problem number 1926, nearest exit from entrance in maze. This problem challenges us to find the shortest path to the nearest exit in a maze, starting from a given entrance. Let's dive in and break it down step by step. In this problem, we are working with a maze represented by a grid of size mxn. Each cell in the maze is either an empty space, denoted by dot, or a wall, denoted by plus. You are provided with the starting position, called the entrance, which is a specific cell in the maze identified by its row and column indices. From the entrance, you can move in any of the four cardinal directions, up, down, left, or right, but only through empty cells. Walls cannot be traversed, and you must also stay within the boundaries of the maze. The objective is to find the shortest path from the entrance to the nearest exit. An exit is any empty cell located on the border of the maze, but the entrance itself cannot be considered an exit. If no such path exists, you should return -1. The output for this problem is a single integer that represents the number of steps required to reach the nearest exit from the entrance. If there is no valid path to any exit, the output should simply be -1. To help clarify, let's look at some examples. In the first example, we are given a maze where the entrance is at position 1, 2. The maze layout and the entrance position are provided as input. From this starting point, we need to determine the shortest path to an exit cell located on the border of the maze. In this example, the nearest exit is located at position 0, 2, and it can be reached in just one step. Let's consider another example where the entrance is at position 1, 0. In this case, the shortest path to the nearest exit, which is at position 1, 2, requires 2 steps. This example demonstrates that the pathfinding process continues until the nearest border cell is identified, and the number of steps required to reach it is counted. Finally, let's examine a scenario where there is no valid exit. For instance, if the entrance is located at 0, 0, in a maze where all potential border cells are either walls or unreachable, the output should be -1. This is because no path exists from the entrance to any exit. These examples illustrate how the problem handles different situations, from simple paths to cases where exits are completely inaccessible. When solving this problem, there are a few edge cases to consider. First, the maze might consist entirely of walls, meaning no movement is possible. Second, the entrance itself might be surrounded by walls, preventing any valid moves. Third, if there are multiple exits, the goal is to find the nearest one, so efficiency in traversal is critical. Fourth, for larger mazes, such as those with dimensions close to 100 x 100, the solution must handle the size efficiently to avoid unnecessary computations. Lastly, remember that even if the entrance is on the border, it is not considered an exit, which can sometimes affect how paths are identified. These cases highlight the need for a robust algorithm to handle both common and uncommon scenarios effectively. To solve the problem of finding the nearest exit in a maze, we can think of it as a shortest path problem in an unweighted graph. In this analogy, the maze cells represent the nodes, and valid movements between cells act as the edges. One possible approach to solve this is using depth-first search, or DFS. With DFS, we systematically explore all potential paths from the entrance by diving deeply into each path before backtracking. To prevent cycles, we track visited cells as we go. While this method is intuitive and straightforward to implement, it has significant drawbacks. DFS doesn't naturally prioritize shorter paths, meaning it might explore unnecessarily long routes before finding the shortest one. Additionally, the recursive nature of DFS can lead to high memory consumption, particularly for large mazes or grids. This makes DFS suboptimal for this problem, especially when efficiency is a priority. An alternative and more effective approach is using breadth-first search, or BFS. With BFS, we start from the entrance and explore the maze level by level. This ensures that all cells at the current distance are processed before moving to the next level, making it ideal for finding the shortest path in an unweighted graph. To implement this, we use a queue to manage the cells to be explored, while marking cells as visited as soon as they are in queued to avoid revisiting. BFS guarantees the shortest path because it processes nodes in increasing order of distance. Its time complexity is O, m*n, where m and n are the dimensions of the maze, as each cell is visited at most once. Additionally, its space complexity is also O(m*n) due to the storage requirements for the queue and the visited set. Another approach we considered is Dijkstra's algorithm, which uses a priority queue to compute the shortest path. While it guarantees correctness, it introduces unnecessary overhead for unweighted graphs like this maze, making BFS the simpler and more efficient choice here. Given these considerations, the BFS approach was chosen as the most suitable strategy for this problem. It is simple to implement, efficient for unweighted graphs, and guarantees the shortest path. By focusing on cells at the current distance before exploring deeper, BFS aligns perfectly with the needs of this task. A few key observations solidified this choice. First, the maze can be naturally represented as a graph, where the cells are nodes and valid movements are edges. Second, in unweighted graphs, BFS outperforms DFS and Dijkstra's in terms of efficiency and simplicity. Third, marking cells as visited immediately after adding them to the queue prevents revisiting and redundant computations, which is crucial for performance. Lastly, it's important to note that an exit is only valid if it lies on the boundary of the maze and is not the entrance itself. These insights collectively highlight why BFS is the optimal approach for solving this problem. Each approach comes with its own trade-offs. DFS, while straightforward, is inefficient for shortest path problems because it doesn't prioritize shorter routes and can consume significant memory due to its recursive nature. BFS, on the other hand, is specifically designed for unweighted graphs, guaranteeing the shortest path while maintaining manageable memory usage. However, its space complexity can become a concern for very large grids, as the queue can grow significantly. Dijkstra's algorithm introduces additional overhead due to its use of a priority queue, which isn't necessary for this unweighted scenario, though it could handle weighted graphs if the problem were extended. Ultimately, BFS strikes the right balance between efficiency and simplicity, making it the best choice for this problem. Its time complexity of O(m*n) is optimal, and the implementation is both intuitive and effective, addressing the problem's requirements directly while avoiding the limitations of the other approaches. In this problem, we are tasked with finding the shortest path from the entrance of a maze to the nearest exit. The maze is represented as a 2D grid, where each cell can either be an open path, represented by a dot, or a wall, represented by a plus sign. The entrance is marked as a specific cell within the grid, and exits are defined as any boundary cells that are not the entrance. The goal is to calculate the fewest number of steps required to reach the closest exit. Since this is a shortest path problem in an unweighted grid, breadth first search, or BFS, is the ideal algorithm to use. To implement this solution, we'll first validate the input by checking the maze's dimensions and ensuring there are valid exits. Next, we'll prepare the data structures, including a queue to manage BFS traversal and a visited set to keep track of process cells, which helps avoid redundant computations and infinite loops. To begin the BFS process, we initialize the queue with the entrance cell, setting the step count to 0, and mark the entrance as visited. The BFS algorithm then operates iteratively while the queue is not empty. In each iteration, we dequeue the next cell, which contains the current row, column, and the number of steps taken to reach it. If the current cell is on the boundary and is not the entrance, we immediately return the step count as the shortest path. Otherwise, we generate all possible neighboring cells by exploring the 4 directions, up, down, left, and right. For each neighbor, we check if it is within the bounds of the maze, represents an open path, and has not been visited yet. If all these conditions are met, we enqueue the neighbor with an increment step count and mark it as visited. If the queue is exhausted and no exit is found, we return -1 to indicate that no valid path exists. BFS is particularly effective in this scenario because it explores all cells at a given distance before moving on to cells farther away, ensuring the shortest path is found. By restricting exits to boundary cells, we maintain both correctness and efficiency in the solution. The visited set plays a crucial role in avoiding unnecessary reprocessing of cells, which not only saves computation time but also guarantees the algorithm terminates. The queue is central to the BFS process, storing cells in the order they need to be processed. Each element in the queue is a tuple containing the row, column, and step count. Operations like enqueuing and dequeuing are efficient, taking constant time. The visited set allows for quick lookups and insertions, also in constant time on average. The maze grid itself serves as the input graph, where each cell acts as a node.
Finally, edge cases such as mazes with no exits, one-cell mazes, blocked entrances, or multiple exits are all handled by the algorithm to ensure robust behavior. Edge cases are an important consideration for this problem. For example, if all boundary cells are walls, the function will correctly return -1, as no exits are available. Similarly, in a single-cell maze, the entrance is also the boundary, so the algorithm returns -1 because there is no valid exit. If the entrance is entirely surrounded by walls, no neighbors can be explored, and the function will terminate with -1. In situations with multiple exits, BFS ensures the nearest exit is found due to its level-by-level exploration. When analyzing the algorithm's complexity, the time complexity is O(m*(n), where m represents the number of rows and n represents the number of columns. Each cell is processed once, and all its neighbors are checked. The space complexity also amounts to O(m*(n), as the queue and visited set can each store up to m*(n) cells in the worst-case scenario. These efficiency guarantees make BFS a perfect fit for this problem. Let's walk through an example to see the algorithm in action. Consider the maze represented by a 3x4 grid, where the entrance is at position 1, 2. Initially, the queue is populated with the entrance cell 1, 2, 0, and the visited set contains just the entrance. The first cell dequeued is 1, 2, 0. From here, its neighbors are calculated as 0, 2, 2, 2, 1, 1, and 1, 3. After validation, the valid neighbors 0, 2, 1, and 1, 1, 1 are added to the queue and marked as visited. Next, the cell 0, 2, 1 is dequeued. Since this cell is on the boundary and is not the entrance, it qualifies as an exit. The algorithm immediately returns the step count, which is 1. This demonstrates how BFS efficiently finds the shortest path to the nearest exit. The final output for this example is a shortest path length of 1. This implementation solves the problem nearest exit from entrance in maze by using a breadth-first search (BFS) approach. The BFS is ideal for finding the shortest path in an unweighted grid-based maze. The algorithm begins by initializing the maze dimensions, rows, calls, and defining the possible movement directions. A deque is used as the BFS queue, initialized with the entrance position. The entrance cell is immediately marked as visited by converting it to a wall, plus, to prevent revisiting. The BFS proceeds level by level, where each level corresponds to one step from the entrance. The steps variable tracks the distance from the entrance to the current BFS depth. For each cell in the current level, all possible moves are checked using the predefined directions. If a neighboring cell is valid, within bounds, open path, and not visited, the algorithm determines whether it is an exit. An exit is any boundary cell except the entrance. If an exit is found, the function immediately returns the number of steps. If no exit is found in the current level, the valid neighboring cells are marked as visited and added to the queue for the next level of BFS. This ensures no cell is revisited, preventing infinite loops. If the queue is exhausted without finding an exit, the function returns -1, indicating no exit is reachable from the entrance. By marking cells as visited during traversal, the algorithm operates in O(m*(n) time, where m and n are the maze dimensions, as each cell is processed at most once. This ensures efficiency and correctness for all edge cases, including mazes with no exits or fully enclosed entrances. Here, we begin by importing necessary libraries and defining our solution class. The nearest exit method takes in a 2D character array maze and an integer array entrance representing the starting point. We determine the number of rows and columns in the maze and define a directions array to represent the 4 possible movement directions: up, down, left, and right. Next, we initialize a queue to perform a breadth-first search, adding the entrance to the queue and marking it as visited by setting its value in the maze to +. We also initialize a steps counter to track the number of moves made. Then, we enter a while loop that continues as long as there are elements in the queue. At the start of each level of the BFS, we increment the steps counter and process all nodes currently in the queue. For each node, we extract its coordinates and iterate over all possible directions to calculate the next cell's coordinates. If the next cell is within the maze boundaries and is unvisited, denoted by a dot, we check if it lies on the boundary of the maze. If it does, this means we've found the nearest exit,
so we return the current step count. Otherwise, we mark the cell as visited by setting it to plus and add it to the queue to explore further in subsequent iterations. Once all possible paths are explored and no exit is found, the function returns -1 to indicate that no exit is reachable. This implementation ensures that we systematically explore the maze while avoiding revisits, making it both efficient and easy to follow. To solve the problem of finding the nearest exit in a maze, we use a breadth-first search, or BFS, approach. Let's begin with example 1, where the maze is represented as a 2D grid. The entrance is at position 1, 2. First, we initialize key variables, the number of rows and columns in the maze, a list of possible movement directions, and a queue initialized with the entrance point. We also mark the entrance as visited by changing its value to plus. At this stage, the number of steps is set to 0. When we begin the BFS process, the first level involves processing the entrance point at 1, 2. From here, we explore its neighbors. For the neighbor at 2, 2, it's a wall, so we skip it. Similarly, 1, 3 is also a wall, so we skip that as well. For the remaining neighbors, 0, 2 is an empty cell, so we mark it as visited by changing its value to plus and add it to the queue. Similarly, 1, 1 is also an empty cell, so we follow the same process. At the end of this level, the queue is updated to contain the points 0, 2, and 1, 1. Now, we move to the second BFS level, where the step count increments to 2. Here, we process the point 0, 2. Since this point lies on the boundary of the maze, it is recognized as an exit. Therefore, the BFS terminates, and we return the total number of steps, which is 2. In example 2, we analyze a maze where there is no exit. The entrance is at position 1, 1. Once again, we initialize the rows, columns, movement directions, and the queue with the entrance point. We mark the entrance as visited and set the step count to 0. During the first BFS level, we dequeue the entrance point 1, 1 and explore its neighbors. However, all potential neighbors 2, 1, 1, 2, 0, 1, and 1, 0 are walls, so we skip all of them. With no valid cells left to process, the queue becomes empty, signaling that no exit can be reached. Thus, the algorithm terminates, returning -1 as the output. Now let's consider example 3, where the maze is larger and has multiple paths to the exit. The entrance is at 0, 0. After initializing the rows, columns, movement directions, and queue, we mark the entrance as visited and set the step count to 0. In the first BFS level, we process the entrance point 0, 0. Out of its neighbors, 1, 0 is an empty cell, so we mark it as visited and add it to the queue. The neighbor 0, 1 is a wall, so we skip it. At the end of this level, the queue contains 1, 0. Moving to the second BFS level, we process the point 1, 0. Here, 2, 0 is a wall, so it's skipped. The neighbor 1, 1 is empty, so we mark it as visited and add it to the queue. The queue is now updated to 1, 1. In the third BFS level, we process 1, 1 and explore its neighbors. From the point 1, 1, we find that 1, 2 is an empty cell. We mark it as visited and add it to the queue. The BFS continues level by level, exploring valid neighbors and skipping walls or visited cells. Eventually, we reach the exit at 3, 4, which is located on the boundary of the maze. At this point, the total number of steps taken to reach the exit is 5. Therefore, the algorithm returns 5 as the output for this example. This demonstrates how BFS systematically explores all possible paths to find the nearest exit in the shortest number of steps. To analyze the time complexity of this solution, let's begin with the breadth-first search traversal. The BFS algorithm systematically explores each cell in the maze, and since the maze consists of rows calls cells, every cell is visited exactly once in the worst-case scenario. This happens when all cells in the maze are empty, meaning the algorithm must traverse the entire grid. Additionally, for each cell, the algorithm evaluates its 4 possible neighbors up, down, left, and right. This neighbor exploration takes constant time, or O1, for each cell. When we account for all cells, the total cost of neighbor exploration scales with the number of cells, which is also O, rows asterisk calls. Combining these, the overall time complexity of the algorithm is O, rows asterisk calls. Now, let's focus on the space complexity. The primary contributor to space usage is the queue used in the BFS algorithm. In the worst case, this queue may hold all cells in the maze simultaneously, leading to a maximum space requirement of O, rows asterisk calls. Additionally, the solution modifies the maze in place to mark visited cells, which means no extra space is allocated for tracking visited nodes. Beyond this, the algorithm uses a small, constant amount of auxiliary space for variables such as directions and counters, contributing O1 to the space complexity. When we combine all these factors, the overall space complexity of the solution is O, rows asterisk calls.
Let's now consider the best, average, and worst case scenarios for the algorithm.
In the best case, the entrance is adjacent to an exit, and BFS completes after checking the first layer of neighbors.
Here, the time complexity is O1.
For the average case, the algorithm explores a portion of the maze before finding the nearest exit, and the complexity is generally proportional to the number of cells visited. In the worst case, where all cells are empty, the algorithm must traverse the entire maze, visiting every cell. Both the time and space complexities in this scenario are O, rows asterisk calls. When comparing this approach to alternatives, we see significant improvements. A brute force method, for example, would involve exploring all possible paths from the entrance to every potential exit. This would result in exponential time complexity, O, for caret, rows asterisk calls, due to the recursive branching into 4 directions at each cell. In contrast, the BFS approach ensures that each cell is visited only once, reducing the complexity to O, rows asterisk calls. While depth-first search, DFS, could also be used, it relies on a recursive stack that, in the worst case, could reach a depth of O, rows asterisk calls. Additionally, DFS is not ideal for shortest path problems in unweighted grids, as it does not naturally explore the shortest routes first, unlike BFS.
Finally, let's establish the mathematical basis for the algorithm's time and space complexity.
If we let n represent the total number of cells in the maze, or rows asterisk calls, BFS ensures that each cell is processed exactly once. For each cell, a constant number of operations is performed, such as checking neighbors and managing the queue. This results in a total of O(n) operations, confirming the time complexity is O, rows asterisk calls. Similarly, the maximum number of cells stored in the queue at any point is proportional to n, leading to a space complexity of O(n). These calculations demonstrate that the algorithm is both time and space efficient, making it well suited for large mazes.
When solving this problem, there are a few common mistakes to avoid. First, forgetting to mark nodes as visited can create major issues. Without marking cells, you might revisit the same cell multiple times or even get stuck in an infinite loop. To fix this, you can either use a separate visited matrix or modify the maze itself by marking visited cells, such as replacing a dot with a plus. Another mistake is not handling edge cases correctly, particularly for exits. Remember, the entrance itself is never considered an exit, so you need to explicitly exclude it when checking for valid exits. Additionally, an inefficient implementation of BFS can slow down your solution significantly. For example, appending and removing elements from a regular list instead of using a deque can degrade performance. To fix this, leverage Python's collections.deque, which allows efficient O(1) operations for both appending and popping elements. Another area where mistakes often happen is overcomplicating the exit condition. Writing complex conditions to determine if a cell is an exit can make the code harder to debug. Instead, use a simple boundary check: an exit is any cell on the edge of the maze that is not the entrance. It's also important to pay attention to the problem's constraints. For instance, assuming the maze is always solvable or overlooking edge cases like very small mazes, such as a 1x1 maze, can lead to incorrect results. Always carefully read the constraints and account for scenarios where no valid exits exist. In interviews, it's crucial to articulate your approach clearly. For example, explain that this problem is essentially about finding the shortest path in an unweighted graph, which is why BFS is the optimal choice over DFS. Demonstrate how you handle boundary conditions efficiently, perhaps by using helper functions or concise loop structures. Lastly, be ready to analyze the time and space complexity of your solution. BFS typically operates in O(m*n) for a maze of size m by n, and this complexity arises from both the Q and the visited matrix. Highlighting how the problem relates to other shortest path scenarios, like weighted graphs or 3D mazes, can also make a strong impression. This problem shares similarities with several other LeetCode problems, which can help deepen your understanding. For example, LeetCode 994, Rotting Oranges, involves grid traversal with BFS to calculate the shortest time for an entire grid to rot. LeetCode 1091, Shortest Path in Binary Matrix, is another shortest path problem, but in this case, you're working with 8-directional movement. LeetCode 542, O1 Matrix, uses BFS to find the shortest distance to the nearest zero in a grid, and LeetCode 286, Walls and Gates, calculates the shortest distance from gates in a grid. These problems share key principles with the maze problem, particularly their reliance on BFS for shortest distance calculations. While BFS is the most appropriate approach here, alternative methods exist. For instance, DFS can explore paths to exits, but it doesn't guarantee the shortest path, particularly for larger mazes, and may run into performance issues. Bidirectional BFS is another option. It reduces the search space by simultaneously exploring from both the entrance and all exits. However, it's more complex to implement and requires pre-identifying all exit points. Finally, for weighted mazes where cells have movement costs, you can use Dijkstra's algorithm. This approach is well suited for scenarios where different paths have varying costs, as it guarantees the shortest path in weighted graphs. However, for this specific problem, Dijkstra's algorithm is generally overkill. Since the maze is unweighted, BFS remains the simpler and faster solution. It's important to balance the complexity of your approach with the problem's requirements, and for unweighted mazes like this one, BFS is optimal. Great job! We've covered how to solve the nearest exit from entrance in maze using BFS, along with its complexity analysis and key insights. Remember, BFS is a handy tool for grid-based problems. Don't forget to like, subscribe, and share for more coding solutions. See you next time, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!